All right, so in this video, guys, we're going to talk about the linearization and differentials. So linearization essentially just means that we are going to take something that's not a line and approximate it by using a line and approximate what it can do for us using that line. It's pretty common to sometimes when you're given a complicated curve to dumb it down a bit, knowing that studying lines are easier, but also acknowledging that it's not going to be the exact value you're looking for, but instead an approximation. So what I would encourage you to do, and you can certainly do this if you pause the video or you can do it later, go to Desmos and type in any curve. Type in y equals cosine of x. You can clearly see it's a very oscillating function with a bunch of curves in it, right? But if you zoom in close enough at one particular value, it's going to appear linear. And so that's the advantage we're going to use. We're going to try to get in close enough to where our approximation is good. So now to do all of this stuff, we're going to have to focus on the equation of the tangent line again. And we know that the equation of a tangent line at x equals a can be given by y minus f of a equals f prime of a times x minus a. So remember, this is your point slope form. Y minus y1 equals m, x minus x1, where at a, we've got our y coordinate at a, we've got our slope being our derivative at a, and then we've got our x minus a. So this is the equation of that tangent line at x equals a. And if I simply add f of a to both sides, then I get y equals. Well, remember, if our function that we're talking about is y equals f of x, then my y is close to what my f of x is, right? This is going to be my line right here. But if y equals f of x, now I'm in a position to where I can say that f of x is going to be approximately f of a plus f prime of a times x minus a, which is in fact a linear equation we'll call L of x. Okay, so our line, our equation of our tangent line is driving this whole thing to give us a linear approximation of our nonlinear function f. Okay, so this guy being the line is approximately our curve here. So I'm going to go ahead and clear the screen. I'll get an example up here real quick and show you what this can do for us. Okay, so the example we're going to look at is to find the linearization of sine of x where a is equal to 30 degrees. Okay, a couple things real quick. I do have the formula back up that we just derived, the linear function that we're going to use to approximate, so you can recall that. And the other thing I want to mention is this a value equaling 30 degrees. In calculus, it should always be alarming to see 30 degrees, knowing that we need to use radians. So we need to use that pi over 6 in this problem. Okay, just kind of a sidebar. So a couple things, or one other thing before I get started, I do want to mention that in this case we are going to need f prime right here, and so the f prime would be our cosine of this guy. So as I write this out, don't forget that. All right, so we've got L of x equals our function evaluated at a, which is pi over 6, plus the derivative, as we talked about cosine, evaluated at pi over 6, times x minus pi over 6. So I'm going to clean this up. Sine of pi over 6 would be 1/2, plus we have a root 3 over 2 of cosine of pi over 6, times x minus pi over 6. So this is, again, this is our linear function now, our linear function that's going to approximate what our function is doing. Now, what I want to do now is take it a step further. I actually want to show you how it approximates. So we're going to approximate sine of 32 degrees. I think most people would agree that 32 is pretty close to 30, but it's not exact. So if we use our linear approximation, our x value is going to end up being 32 degrees, which ends up converting to 8 pi over 45 radians. So L of 8 pi over 45 is going to be equal to 1/2 plus root 3 over 2, 8 pi over 45 minus pi over 6. And you could certainly use a calculator on a problem now at this point, but that's going to give us now 0.5302. And so what I want you to do is I want you to take a calculator out, and I want you to take sine of 32 degrees. So a sine of 32 degrees, or sine of 8 pi over 45 radians. And your calculator should give you a number that's really close to this. I won't be exact, but it'll be really, really close to this. And so we went ahead and approximated sine of 32 degrees by using the line created by looking into our function sine of x at a very, very close similar angular measure. So kind of an interesting application, I think.